Lecture 6.2, the Fourier transform. So the following was generated from a Jupyter notebook, so this is the one. And I don't think I have posted it yet, but I'll try to post it so that you guys can see the source if you like. We begin with the usual loading of modules. So I'm going to do this Fourier transform lecture by showing you guys sort of how to plot the Fourier transform or a Fourier series that approaches a Fourier transform. So that's kind of where we're going. We're going to go from a Fourier series to a Fourier transform. So let's consider a periodic function f with period t. Each period, the function has a triangular pulse of width delta and height delta over 2. Okay? So for this example here, I'll have the period defined as 15. I actually do several periods in the plot that we'll look at. So this code just shows you how to do it for one frequency instead of 3 frequencies. Okay, so pulse width will define as 2. So first, we'll plot function f in the time domain. So this pulse train function, we'll do that. I create a little lambda function that gives me just like a nice little mathematical statement that allows me to just plug in some value into f. So this is like a MATLAB anonymous function, right? And then I use mod to decide in which part of the period we are. And then I say, okay, if you're less than pulse width over 2, you're going to be on this, essentially this pulse width over 2, height minus the absolute value. That gives us that triangle. So negative absolute value is a sort of downward V shape. And that's what I use to give us that triangle pulse. And then once we get up close to the end, I'll go back up. So the ramp down is first, and then the ramp back up is at the end of the period. And that's what we return depending on which part of the period we're in. So now we develop a numerical array in time to plot f. So 201 points. I'll in-space it, do just like a couple periods, and we'll compute what the points are. I should probably turn this pulse train function into a vector function. Probably would have higher performance, but I think it's harder to read. So I thought I would just do it with a for loop instead, because it doesn't really matter how fast it is. So then I just do a simple plot, and the result is given. Oh, jeez. Oh, it didn't plot. Well, that's great. Anyways, it looks like one of these. It's like one of those. Triangle. Okay. All right. So very good. For delta equals 2 and these different periods, the left-hand column of figure 6.1 shows 2 triangle pulses for each period. Doesn't state it very well, but essentially it shows 2 periods of the triangle pulse. Okay, so this first one, the period will be 5 seconds. The second one period will be 15 seconds, and the third one period is 25 seconds. Obviously, I'm zooming out here so that I can fit 10 seconds, 25 seconds, etc. So the width getting thinner is just due to that. The actual width is the same in all these. It's just the depiction is zoomed out in the x-axis. So in order to fit 25 seconds on it. Okay, and very good. Okay, so consider the following argument. Just as a Fourier series is a frequency domain representation of a periodic signal, a Fourier transform is a frequency domain representation of an aperiodic signal. We'll rigorously define that in a moment. The Fourier series components will have an analog then in the Fourier transform. Recall that that they can be computed by integrating over a period of the signal. If we increase the period infinitely, the function is effectively aperiodic. Okay, so we say, okay, this pulse happens, this triangle pulse happens at 0, and then the next time it happens, we take that out further and further. So you see how in the plot, like we're zooming out and it's at 25 seconds. Say you went to 25,000 seconds, 25 million seconds, and take it out to infinity. It's effectively just a single pulse at the origin. Okay, so if we take that next pulse out to infinity, if we take that period out to infinity, effectively what we've done is created a waveform that's actually just aperiodic. It doesn't repeat because the next pulse doesn't happen ever. So, okay. The result within a scaling factor will be the Fourier transform analog of the Fourier series components. Let's approach this understanding by actually computing the Fourier series components for increasing period t using the equation above that we already used for computing those. We'll use SymPy to compute the Fourier series cosine and sine components an and bn for components n and period t. So this was A0 separately, but you can just do it A0 using the same formula, so I just commented this out. I define some SymPy variables, and I tell SymPy if they're real variables, positive or non-negative. So real can be negative, 0, or positive. Positive, non-negative, or different. And SymPy will simplify based on what it knows those symbolic variables are. So it will not make assumptions about it unless you specify, like, so a lot of times, like our constants are going to be positive, always positive. So they'll be positive or 0. So if you specify that early, it helps the simplification later. So that's one of the caveats when you're using SymPy, is to do that up front. So I use integrate to integrate over a period to find the ANs, and do the same thing for the BN using the sine. So cosine for AN, sine for BN, and I get a pretty nice output. I mean, it took me a little finagling to get it here, but SymPy does a nice job of recognizing that doing a piecewise representation here is actually pretty useful. So it did the piecewise representation. I didn't have to tell it to. Pretty smart. Yeah, I was surprised. I was like, we're gonna see what happens here, and sure enough, that's what it spit out. This is not me typing this equation in. It's actually auto-generated. It's pretty sweet.
Oh, the result will just explain that for us.
Pardon?
SymPy will display the...
Yeah, LaTeX. It'll do LaTeX. So if you do it in a Jupyter notebook, it'll display it as LaTeX. Oh, pretty sweet. So the BNs are always 0, and the ANs are non-zero. Now, that's not surprising. Well, it's not surprising that BN is 0. Why is that?
Because it is an even...
It's an even function. Yeah, so we knew that the BNs had to be 0.
Odd function. When it is even, A must be 0. Is that what we say?
Yeah, but not every function is even or odd. You can be neither also. So sometimes you need both. But if you can arrange it so that it's even or odd. So there's that. Okay, so let's compute the harmonic amplitude then from the previous formula, and we'll display it here. So we get this absolute value coming in because we took the square root and squared things, so get an absolute value. And now we lambdify it so that we can use NumPy to plug in numbers and give us a graph. So lambdify is pretty easy. You just say, hey, you know that function I have, Cn, I defined up here symbolically, I want to be able to plug vectors into it or arrays into it, NumPy arrays into it, and get out arrays. So did that. Now we can plot. So bang, 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 do some plotting. And that was just for one of these, but I generated 3 different cases. So the time domain representation and then the frequency spectrum plot, so the CNs. I scaled the CNs by t over delta, which allowed me to represent it on this plot in a nice way. Otherwise, the scaling changes on each one of these, so the vertical scaling is going to change here. But what it looks like is that there's some continuous function that's emerging as you move t out further and further. You're getting greater and greater density in your frequency spectrum, in your line spectrum. So that line spectrum gets denser and denser as you move t out, as you increase your period. And if you go to infinity, it gets infinitely dense. Okay, that's kind of the idea. It gets infinitely dense. The line spectra are shown in the right-hand column. Note that with our chosen scaling, as t increases, the line spectra reveal a distinct waveform. Let f be the continuous function of angular frequency omega here, 613. Mystery function, pulled out of nowhere. If I plot it, would you look at that? It's the function that's emerging here. It's emerging. How did I do that? So it's the function that's emerging from increasing the period. Now we're ready to define the Fourier transform and its inverse. So this is how you would actually find out what that function is that's emerging. It's the Fourier transform. And if you want to do Fourier analysis on an aperiodic function, y of t, you can find a of omega and b of omega by doing a very similar integral. Instead of integrating over a finite period, you integrate over the entire domain of y of t. And we are using the cosine multiplier here, a sine multiplier for b. And synthesis is, instead of an infinite sum, it's an infinite integral over the entire frequency domain to give us the time domain back. The complex form of it is also very analogous. So we have the Fourier transform, and then the inverse Fourier transform is what we call the synthesis side of it. So they have the transform, which goes from time domain to frequency domain, and then the inverse transform, which goes from the frequency domain to the time domain. Okay? So that is this. So whereas in the Fourier series, a lot of times we would use the trigonometric form. The trigonometric form for the Fourier transform is rarely used. And you can see why. It's kind of messy. Don't really like that. And the complex form is nice and compact, and it has this nice symmetry to it. So this is the form that most people use. So we defined it. There are many applications for this, including solving differential equations and frequency domain representations called spectra of time domain functions. So you can take like a Dirac delta function, a unit step function. These things are aperiodic, but they still have Fourier transforms associated with them. So the Fourier transform is really nice. Reminds us of the Laplace transform, doesn't it? So this has a striking similarity between the Fourier transform and the Laplace transform, with which you are already acquainted. So you guys have all seen the Laplace transform, more than you've seen Fourier, most likely. In fact, the Fourier transform is a special case of a Laplace transform, and with Laplace transform variable s equals j omega. So remember, s is complex with a real part and an imaginary part in the Laplace transform. In the Fourier transform, it's just imaginary. So instead of having some real component, it's just imaginary. Both transforms, Fourier and Laplace, convert differential equations to algebraic equations, which can be solved and inversely transformed to find time domain solutions. The Laplace transform is especially important to use when an input function to a differential equation is not absolutely integrable, and the Fourier transform is undefined. So you have to have absolute integrability for a Fourier transform, whereas the Laplace transform relaxes that requirement. So for example, our definition will yield a transform for neither the unit step nor unit ramp functions, because they don't have, they're not absolutely integrable. They continue to, as you go off to infinity, continue to grow. So the absolute integrability is problematic for some functions that we like. So that's part of why we like Laplace transforms, is that you can do Laplace transforms of those functions, and they're nice. They're not messy. However, the Laplace transform is preferred for initial value problems due to its convenient way of handling them. For a transform, you can do it, but it's less nice. Two transforms are equally useful for solving steady state problems. Although the Laplace transform has many advantages for spectral considerations, the Fourier transform is the only game in town. So people don't talk about, like, what is the plot of your Laplace domain S. Like, you don't want to see a plot versus S. You want to see it versus frequency. So that's the variable that has a physical interpretation that makes more sense, because frequency is the imaginary component, and that's the component that has some tangible or real quantity associated with it. Okay, a table of Fourier transforms and their properties can be found in Appendix B2, so I recommend you check that out. It's your pretty standard Fourier transform table, and it also has properties in it. So I didn't get into the properties of the Fourier transform. As we need them, I'll introduce them, but we're mainly introducing this in order to do PDE solutions. And I know you guys are familiar with the frequency domain. You know and love it. You guys want to review Bode plots again. But alas, we're not doing that this time. Now we're going to move on to doing orthogonal functions and then PDE solution. So, all right.